Yeah, thanks everyone for staying till Friday. I myself missed a couple days of the conference, so I hope I'm not going to repeat too much of what other people said, but I suspect not. So if you haven't met me or if I haven't met you before, I'm Roger Melko at the University of Waterloo and Perimeter and Super Theoretical Physics. I'm a condensed matter theorist, and so I hope I kind of hit the right level with what I'm going to talk about today. And really what I'll focus on is what I'm calling language models, but it's a class of generative models that we've been constructing to aid in what I'm calling quantum simulation. So quantum simulation is kind of a broad bucket term that could include simulating matter on quantum devices, like quantum computers, analog quantum computers, or it could mean simulating quantum mechanics using classical algorithms. This work on language models of like many things in our field started with Juan Carrasquilla, who after summer school we had taught in Brazil, in ICTP in Sao Paulo, had basically been working on generative models for reconstructing density matrices from POVM measurements. And what Juan had observed is that a certain type of recurrent neural network, so that's where the language model part comes from, did really well in terms of this reconstruction in these classical algorithms. And so that was sort of the genesis of many more papers and the careers and projects and so on of many more students, both at Perimeter Institute and also at the Vector Institute for Artificial Intelligence, where Juan is until January. And in particular, I want to point out the contributions of Mohammed Hibat Allah, who's a student that we shared, who really took this idea of recurrent neural network wave functions and ran with it for his PhD, and he's now teaching faculty at Perimeter. So I wanted to start with just a real quick slide about what I think is some of the most interesting problems in quantum computing. So I mentioned I'm a condensed matter theorist, but I don't know, as I get older, I slowly seem to be transitioning into a condensed matter or AMO experimentalist, because I really find the devices that we're building today fascinating. And I really want to be part of this grand challenge of, I think, building these quantum simulators and quantum computers. So there's two architectures that I work most closely with. One is at the Institute for Quantum Computing, and I'm not going to talk too much about it, but it's a set of ion trap labs run by Rajabul Islam and Crystal Senko. So they have a couple species of ion, and I just got this off my iPhone, but I've been taking pictures of the optical tables for 5 or 6 years now, ever since they came to IQC. So it's been really rewarding to see these experiments develop. And I also work very closely with Rydberg atom array hardware that's based mostly in Boston and some groups in France, which are very interesting. This is my student, Roger Luo, at QERA. This is us. I just wanted to convince you that they actually let me step in a laboratory, although it's like, don't touch anything, obviously. But what we've been doing with QERA, and particularly Roger Luo, is working a lot on their control and readout stack. And so there's a ton of interesting problems in quantum computing related to control. There's many exponentially hard control problems that we don't even talk about in typical conferences like this, that really have to be overcome, probably with some sort of breakthrough before we can do things like, address and entangle multiple qubits and all sorts of things. So, with all of these challenges that are kind of, inherent in these devices, the one I just think would like to focus on is sort of the data acquisition rates. So we do a lot of work with data that comes out of these experimental devices. And the data itself is, of course, very interesting. It contains information about the quantum state that's being prepared. And it's pulled out of these machines at very different rates. And so the superconducting quantum circuits that you maybe are familiar with, Google, IBM, Rigetti, D-Wave, they're actually very fast data acquisition machines. What I heard about Amazon's machine over the last few days, here at Caltech, or up in Caltech, is you're basically talking about 10 to the 7 shots per second, 10 to the 6, 10 to the 7, something like that. These are among the fastest data acquisition rates. And by shots, you can imagine something like a projective measurement or POVM or something like that. But we're just going to have simple projective measurements. Trapped ions are slower, but they're still fairly good. You're getting 10 to the 3 shots per second out of most ion architectures. There's ways of speeding this up, depending on a lot of details about lasers, which I never hear the end of, you know. And the architecture I like actually most has the slowest shot rates. It's 1 shot a second or 3 shot a seconds out of these neutral atom devices. So it's really interesting because these neutral atom devices are now crossing the threshold of thousands of qubits. Like, you know, I was in Boston last week and I've seen, you know, images of, 400 qubits easily being entangled by these machines. They have coherence times of the orders of seconds. Question?
I wanted to ask this to someone, but if you measure one observable, you can get those rates, right? But let's say you switch between observables. Do you have a feeling at the moment? Do you know what I mean? Like, is there a big...
This is a shot for one projective measurement.
But if it's like is there a difference in measuring like 10 to 7 shots with one observable or 10 to 7 shots with, like, let's say 10 to 7 observables or like 10 or whatever? Do you know what I mean? Like, because sometimes like...
What's an observable for you?
Yeah, you're right. You always measure kind of like poly...
I'm just thinking poly, binary measurements and poly basis.
Okay, so then this question is actually... Okay.
Yeah, but I'll talk more about it, yeah. So that's kind of the point is, okay, if we have this type of limitations, so especially I'd say the fastest scaling machines have the slowest data acquisition rates, okay? So it's very hard to probe the internal quantum state. So how many projective measurements are required to construct, so I'd call observables something I would reconstruct from these measurements, an expectation value, maybe is another word for it. And if I can't fully reconstruct observables, then what's the point? What's the value of limited data coming out of these machines? Okay, so that's kind of the theme.
Can I ask a question whether I understand this correctly? So you have really hundreds of qubits, and you just don't know what they're doing because you can only probe them if you have many of these shots.
Well, what I want to convince you is that you still can probe the state, but not in something like a tomographically, like the quantum state tomography sense. But, this is the problem. This is the catch-22. If you build a quantum computer with 10,000 qubits or 1,000,000 qubits or 10 to the 23 qubits, you can't perform tomography on it. So how do you know what it's doing? And we're at this really interesting phase.
I agree. That's exactly
yeah. So that's what this
talking
talking about.
But you don't really know what to do with it. These numbers alone are not everything you have to know.
So I think we take some inspiration from our classical machines. So not, when you build a chip in a foundry, not every transistor is tested. There's some sort of test unit, there's testing suites that occur and so on. But so anyway, that's the point. This is literally the point. We're at this stage now where these are the computers that we have, and they're extremely difficult to build, and there's lots of control and readout problems, okay? So there's a huge effort going into trying to understand the states that today's quantum computers are producing. And how do we do that when we have limited data? In some sense, they're all data limited. So the tools we use are generative models. So I'm going to explain a little bit. First, nice outline, two points, very simple. I just want to talk a little bit about the architectures that we've been developing. So we do actual machine learning. All those students and postdocs I showed you were coding every day. They're using PyTorch, TensorFlow, whatever they're using. And we're training models to prepare them for this data as it comes out of these experimental devices. And then I'll show you specifically applications of the Rydberg atom arrays, which again are some of the largest numbers of qubits and some of the slowest data acquisition rates. So I find them really interesting. Okay, so just to start, just to set everyone on the same stage here, and this may be, completely evident to everybody, but the setting we're thinking about is density estimation. And the quantum computer is that black box, and inside of it is a wave function or a density matrix or some state that's been prepared with some circuit or whatever. I really don't care. What comes out of that is shots, and each one of those vectors x, has n different binary instances, which is coming from n qubits, and which could be rotated into different poly bases or whatever. If you just have sort of one basis setting, really all you're pulling out of there is the Born distribution, right? And so what you're really looking at is the distribution of measurement outcomes of something like a projective measurement. And that's a typical setting for what we're doing with the generative models, which is literally just trying to learn that unknown probability distribution in that black box. And if you're lucky, you can reconstruct something like a a pure state or a mixed state or something if you can rotate, cleverly inside that box to different bases and so on. So the entire setting is really taking that data and then using it to fit parameters in what I'm calling a model. And the model is something that's parameterized, and I'll use lambda, just to, be a catch-all for like all the weights and biases and all this, all the structure that goes into all these various generative models. And so really, in some sense, what we want to do is we want to match the distribution that's encoded in that model, and I'll show you how that could be done, with the black box distribution as close as possible. And then once I do that, say if I did that perfectly, right, that I could use that model to generate additional shots or to, calculate the expectation values of observables or whatever I want to do with it, right? So how do you do that? Question.
I just have a quick question about language, because I think of generative models and density estimation as like different things, in the sense of, I think of density estimation as learning a function which can evaluate the probabilities, and a generative model is learning something which can output samples. And so here you're like interested in models which can generate more samples so that you can do expectation values and things like this. But they'll be implicit in the sense that you won't have access to the probability distribution.
Won't have access to what?
To the probabilities of the strings.
So the models that I'll use will have an explicit representation of the distribution. So I would say implicit versus explicit. Again, you have no explicit representation or parameterization of a probability distribution. In an RBM or an RNN or a transformer, you do. So I'll talk about that, yeah. So one other point is we have a loss function, Kullback-Leibler divergence, or a maximum likelihood, of course. And all of these architectures rely on some version of stochastic gradient descent as a heuristic for training. And I'll return to this several times because this is, in some sense, the important part of what we do is all tied up in this, I want to say black box, but don't be confused, in this, sort of unknown dynamics of training. So the other point about just generally these models that I'm going to talk about is that they can also have a loss function that isn't data driven. You can also have loss functions that are driven by your understanding of the interactions within the device. So if I have connected all my qubits in that black box with a Hamiltonian, and I'm fairly confident that I have the right Hamiltonian, for example, you can also drive these things variationally. So we very much emphasize architectures that can be driven both with data and variationally. And that opens up a whole world of sort of possibilities in terms of training these things. Okay, so that's just kind of the simple setting. Okay, so back to this question about do you have access to the probability distribution? So I very much am looking at the branch of, I think, what Ian Goodfellow would call, if you have maximum likelihood, you have, so it would be implicit and explicit.
Sorry. Can I just say something with the previous slide? Because the last thing, plugging in the structure of the Hamiltonian into the loss function assumes you can compute these things, right? But
assumes you can compute these things.
Like this expectation value of each target sub lambda, right?
Yeah, so how would you compute that in a generative model? You sample the model and calculate the expectation value of the Hamiltonian, given the instantaneous value of the parameters.
H is the quantum Hamiltonian of the physical system, so they should be intractable, right?
Well, there's many things that are intractable that we routinely do. So this is routinely done.
By the way, what is TS of P lambda?
P lambda just means it's parameterized.
Oh, PS of P lambda.
PS.
Temperature.
Oh, this is the entropy.
Okay.
Yeah. So if you want to do if you were quantum mechanical at zero temperature, then it's just the the standard variational setting, which Quan and Giuseppe do routinely again. But it's a good point because how accurately do you need to calculate the expectation value of that Hamiltonian? If it's going into the gradient and the stochastic gradient descent, not very accurately is one point. But this is on my next slide too. So in 2016 or 20 whatever, a lot of us were working on energy-based models, which are on this. I was talking about this branch of implicit versus explicit density models, and then Ian Goodfellow has tractable and intractable. This would be what he would call an intractable generative model, an RBM. And check out Brandon's poster if you want to see more about the RBM. But RBMs are really great for this because they're very, in some sense, easy to interpret. They're easy to imagine how you encode entanglement. They have a visible layer, which there's one Ising variable per qubit. And then they have a hidden layer, which is the latent, in some sense, representation that you can vary. You can make it systematically bigger to make sure you're capturing enough entanglement. And if you have a very kind of trivial system, you can make it smaller and so on. So just this idea that you have some sort of like visible and hidden states that are connected via an energy, which is just the Ising Hamiltonian here. X is visible, H is hidden. Defines a probability distribution. Oh, this should be a joint distribution between X and H. And then you marginalize out H, and you get the thing that you want to match to the black box. Simple as that. And you have model parameters. So the big point with energy-based models is they're intractable because you don't have this normalization, right? You don't know the partition function. And so therefore, if you want to do something like sample, which you have to do, again, if you want to calculate the expectation value of the Hamiltonian, or if you want to turn these things into a generative model, you really require Markov chain Monte Carlo, which I always thought was great. I love Monte Carlo. I do it every day. But the point is that the generated samples in this type of energy-based model or any energy-based model are autocorrelated in Markov time, right? So you just think of single spin flip Ising models, and you flip one spin, and those two states are highly correlated. So there's this idea of autocorrelation time that you have to overcome, and if it's 200 Monte Carlo steps, if you could had a procedure that produced exact independent, IID distributed samples, you wouldn't have to have that Markov chain. So what I'm really, in some sense, calling language models are autoregressive models. And autoregressive models overcome that by representing the joint distribution, through that chain rule of probabilities, which means that, here's my X, here's my qubit states, here's, projective measurement up, projective measurement down. I've now sort of arranged that on the bottom, going into some autoregressive model. And what is output is the conditional probabilities of the next qubit, down this sequence. Because the point with autoregressive models is you really have to break up all of the conditional distributions into some sort of sequence in order to, throw them inside of this product. So that's general, very general. You can break it up into any sort of sequence. And once you do that, the joint distribution is normalized, okay? And so it means that anything you produce, any samples you produce come out completely independently, which is fascinating. But it does require this definition of a sequence. So. Questions on this?
Silly question. So this is enormous in size, right? I mean, this matrix of conditional probabilities. So how do you actually represent it?
Okay, so yeah, so let me show you. Let me show you some typical representations. Maybe in 2 slides. So just to bring us back to language, and I'm thinking of transformers and other autoregressive models. Of course, not all generative models in industry are autoregressive, so diffusion models and so on aren't, right? So that's the big exception. If you ever hear Jan LeCun talk and he's saying, autoregressive models are dead, let's go back to energy-based models. Just think of all the amazing things that flows and diffusion is doing, and you can maybe see his point, but I'm still stuck on this, so. Was there another question? So what's the language part? Okay, so in a language model, you have a sequence of words you're drawing from a dictionary, and if you've never done it, look at Google talk to transformer and start typing in like the prompt. And if I was sampling from the local Hilbert space of some language, I would just call that a vocabulary, and I could pull out a word from a vocabulary, and in the generative model, what I would get out is the conditional probability of the next word in the sequence, and so on, until at some point, we can generate and continue generating as long as we want to, new samples drawn from whatever that joint distribution is that's hidden inside here. As I turn this into a quantum, simulation problem, the simplest thing to imagine doing is just reducing the size of my vocabulary to the outcomes of the projective measurements, spin up or spin down. You could be more sophisticated, it could be POVM, you could have different bases and so on. But really exactly the same idea. You can exactly adopt the architectures from industry and just output the conditional probability distributions for the next, qubit in that sequence, however you define it arbitrarily. And again, I'm saying sequence, but I'm really thinking of a spatial, array of qubits that exist in some experiment or so on.
So is there a clear way how to put it into 2D structure? Because then you would obviously cover a lot more architectures.
Yeah, so that's my next slide. Yeah, it's good. Everyone's following. I love it. Oh, sorry. I'll get to that point. So yeah, so the RNN was the first architecture that we used that wasn't an RBM for this this procedure. And RNNs were basically the go-to for language models until transformers came out 2019, 2020, when it was observed that transformers give better performance by many metrics. The RNNs are very much tied to this idea of a sequence. And you don't have to get into this if you don't want, and apologies, my X's are now sigmas, because I was too lazy. I just cut this out of Mohammed's paper. But okay, so an RNN is in the simplest setting, a set of nonlinear functions that have parameters inside of them. And what they do is they transform two things. They transform a sampled state, so this is your qubit measurements, and they take in what's we call a hidden vector. And that, you should think of the RBM and the idea you have a latent space and some sort of hidden representation that you can vary the size of to get more expressiveness. So if you need more entanglement, you need a bigger hidden vector and blah, blah, blah. But this recurrent cell, with the green can be the same for every one of the elements in this sequence. Really all it does is it outputs a new hidden vector. So if I input, hidden vector 1, what it outputs is hidden vector 2 based on some nonlinear function, weights. There's a weight matrix and a bias matrix. This goes into yet another parameterized representation passed through a softmax. That's why you get a normalized conditional out. And then this is your normalized conditional. Okay, so what happens here, you put in the value of, say, spin 1 that you want. This outputs a hidden state that you don't observe, really, you don't care about. And then in another direction, you take the hidden state, push it through that softmax, get your conditional distribution, sample that, and then consume that sample in the next iteration. So you go through one by one and basically consume those samples. And again, there's lots of ways of generalizing this to include a phase or to include, a mixed state so that you have a density matrix representation and so on. And I think probably one of the best performing ones is still Juan's original POVM architecture. It's just a little, it's just a little different in some sense. But there's also very simple architectures for pure states that, you have a soft max and you have a soft sign, and then you're getting a phase out, and, there's all sorts of different ways of parameterizing phases, let me put it that way. So these things are good representations of quantum states. They're highly expressive. Any data that I get from a quantum computer has, basically have no problem in terms of the number of weights and biases here. And there is some scaling studies on these things. I'm a condensed matter theorist, so always got to scale everything towards a thermodynamic limit and see how it performs and so on. But these are generally have good scaling properties. Okay, so back to your question about the sequence. So what I just illustrated was the typical language setting, and now my autoregressive sequence is red, my red dashed line. So you always have to have a one-dimensional sequence. And for those of you that do DMRG, maybe you're starting to get worried that this is just a reinvention of DMRG, but I want to convince you that it's not. DMRGs are also autoregressive, and MPS is also autoregressive, by the way. But it has a different architecture for how it encodes the state, if you will. So hickory dickory dock, it's all fine. The sequence follows the way that you pass the hidden states. But as we get away from languages and we start thinking about two-dimensional qubit architectures or higher dimensional whatever, the point is that you don't need to be, the hidden state passing doesn't need to be married to the sequence. It has to be causal, but it doesn't have to correspond one-to-one. So in principle, what we use, in practice, what we use especially on the two-dimensional Rydberg arrays, are structures that look like this. This is like the idea of a 2D RNN. So I have hidden states that are being passed, but along the sequence, but I can also pass hidden states that aren't completely aligned with the sequence, essentially. So what happens is, every time that I take a hidden state, I consume the previous, in the nonlinear, the previous hidden state and the sampled qubit state, essentially, it goes through this nonlinear function. And so you have many, many of these nonlinear transformations. If I want to encode entanglement, between this qubit and this qubit, somehow I'm also, taking all of the hidden states that I've passed through this part of the sequence and performing these nonlinears on it. So the restriction in these types of RNNs, it's related to causality of that sequence. You can basically generalize this to pass hidden states, given some unit here. You can pass hidden states to it as long as you're in the past in regard to the sequence. Okay, and that all in general that works fine, and you can encode as much sort of long-range entanglement and kind of in principle as you want. And then the question is, kind of in practice, how well does that work for encoding long-range correlations, long-range entanglement?
So the red arrows are still sigmas?
The red arrow is, where did I? When you break up the conditional, you have to start with 1, 2, 3. So that's what I'm calling the sequence. So there's always a one-dimensional sequence in the chain rule of probabilities, right? So here it's illustrated, again, if you really just have a one-dimensional system, the autoregressive sequence and the passing of the hidden states kind of always corresponds, but they don't have to, is what I'm saying. But you always have to have that sequence defined. Yeah, so that's where transformers are different. So I'm not going to say too much about transformer architectures because I don't know too much about them. This is one of the, I'll get to your questions. This is one of the beauties of working with, Vector Institute for Artificial Intelligence and Machine Learning people and so on is, I was just visiting Juan one day and the director of the institute came to me and was like, have you ever heard of a transformer? And I was like, I have no idea what you're talking about. But, back in 2018, after this paper, Attention All You Need came out, it was clear that transformers were going to be the kind of dominant architecture in generative modeling. Question?
So I was saying, like, in the autoregressive model, can you do it on like trees, or does it have to be a one-dimensional sequence?
You have to have a one-dimensional sequence in order to have a normalized joint distribution come out. Okay? You never hear about the sequence in transformers because most practitioners, I say, don't really think it matters that much how you define that sequence. It's relatively arbitrary. And the point here that I wanted to make with, read the paper if you want. I'm going to talk about encoding, decoding architectures a little bit. But okay, obviously it's not as nice as an RBM, not as nice as an RNN, but there's something to all this architecture if you want to look in it. But really the point is that inside of a transformer architecture is something they call a attention mechanism or masked self-attention, which is really just encoding all pairwise correlations explicitly in some sort of parameterized, if you will, matrix, okay? So what I'm saying is that instead of like in the RNN, where you have to, push all of your, correlations through these nonlinear transformations, they're all explicitly encoded, and Juan and some of the variational experts have ideas about how these relate to Jastrow wave functions. So,
I just venture a comment. So the cool thing about transformers was always that they keep in their internal representation a vector that represents every single input. And I wonder if there are applications where this is really cool, where you want the spin to be represented by something because you only want to read out something about that spin. That could be that's how they do language or word embeddings with transformers, right?
Yeah, definitely.
That could be super cool, actually, to try that.
Yeah, interesting comment. And these are really very much underexplored, I would say. There's tons of research to do on transformers. The point with the mass self-attention is that you do, like I was saying, for given a qubit n, here's your sequence, so the output probabilities are still conditional on the top of the transformer. What goes in is your prompt, and this for us would be, it's the qubit, it's the distribution of, it's one snapshot or it's one sample of the distribution that matches that prompt. It goes to a positional encoding. The latent space from the embedding, the encoder goes into this layer here, and out pops these conditionals up top. So there's still a sequence. But the attention layers, and it's masked causally here, but the attention layers allow all pairwise correlations to be encoded, and then it just masks some out when you need it for the sequence. So they're very different than transformers in that sense, or than RNN, sorry. What the beauty about them is they demonstrate, again, since 2019, 2020, vast performance improvements over RNNs, and what the community, I think, calls scalability and especially emergence, which I love as a condensed matter physicist. And I just threw up, this is a fairly old model now, but kind of an interesting paper from 2020 that showed the performance of transformers. And let me go quick, but just the idea that they're highly parameterized, you can get huge numbers of parameters. And as you increase the number of parameters, your actual performance gets better. So big models can be trained on a fairly small number of tokens. And remember, tokens are just words or qubit outputs or whatever. And also, as you train these things, they demonstrate emergent properties. So they scale. And I find this amazing, but as you push through flops, so floating point operations, not floating point operations per second, so floating point numbers, as you push through like 10 to the 22, 10 to the 23 floating point numbers, there's huge jumps in the accuracies of these transformers things. So, that number, Avogadro's number should ring a bell. And it's incredible that we have machine learning architectures that we are basically training on an Avogadro number of floating points that display some kind of emergence. So I think for us, that's something. I see a head going side to side. I think I think this is one of the things that we should aspire to, to observe emergence essentially in quantum phenomena. So let me move on to the actual data. Just a couple points, I can get back to them. Again, we have autoregressive models that are super powerful. We have different cost functions, and I want to emphasize that the different loss functions have very different training characteristics, and I'll get back to that. The concept of ergodicity, if I move away from a Monte Carlo-based sampler, is in many ways transferred to the loss landscapes, right? I'm parameterizing the loss functions, and I have to find parameterization that gives me a minimum. And this has all sorts of applications also in classical physics and so on. And so Estelle Inac, who's a postdoc at Perimeter, is very much pushing these types of architectures for spin glasses. If you're in if you want to find the lowest energy instance of an Edwards-Anderson Ising model, and or sample around a sort of global minimum, there's no ergodicity issues in the sampling. The ergodicity is in the loss function, if you will, the optimization of the parameters. And we've been doing quite a bit of work on the sequence ordering and how it affects training. And I don't have time to show you, but there's all sorts of different sequence paths that you can imagine doing for, say, a two-dimensional qubit array. And again, this really affects your training. And this isn't something you would see a lot in the machine learning literature. Often there, your sequence is sort of well-defined, especially if it's words, right, that you're speaking. So it just points to things to keep in mind.
How big are these models compared to the classical models?
Right, so classical models are over 1 trillion parameters now. And we're training models.
I'm asking, maybe it stops mattering when it's big enough. Is that a possibility?
It's possible, yeah. Yeah, so we're nowhere near this. The reason we're nowhere near this is because to push this many flops through these models cost tens to hundreds of millions of dollars. That's just in compute time. So boil it down to how much dollars per cycle. And scaling and emergence happens at sort of an industrial scale in these large language models. So we're certainly nowhere near that yet, but it's, again, something to aspire to. Cool? Get on to some quantum computing. All right. Okay, so how do we use these things? I love Rydberg atom arrays. I don't know why. They're just really clean systems, long coherence lengths, seconds. They're highly pure ground states, very low noise, very low sort of measurement error. What they are is you basically trap rubidium as the typical atom in an optical tweezer. So you think about, when was it 2018? Was the Nobel Prize for optical tweezers. Now there's thousands of optical tweezers that can be manipulated spatially and in intensity and moved around in real time. And each one of those can trap an individual atom. That atom can be excited by a laser pulse into n equals 100 principal quantum number or something like that, which gives what they call the Rydberg state. So there's your spin up and there's your spin down. Basically, that's your two-level system. They're strongly interacting. These Rydberg states see each other, and so they're strongly interacting. They have good, high-quality projective measurements. Basically, just take your iPhone and take a picture of them. Well, it's a little more complicated, but they're just CCD cameras. And they're great for analog, I would say state preparation to look at phase diagrams. So they're very much, to me, look like a condensed matter system that you're building from the ground up instead of some rock that you find, in the desert. So I really like that. So I'll mostly think about them as analog quantum simulators. But these actually, I was again last week I was in Boston and I saw some really incredible digital circuits that they're producing. I guess I'm being recorded, so I won't say. But I'll tell you guys in break how many logical qubits that they have been encoding into these things. Rydberg blockade Hamiltonian. So the basic, you put atoms in these tweezers, and this is what they interact with. Okay, so I'm just writing, the ground state and Rydberg state. Ground state, highly excited state. N is the density operator for the Rydberg states. So this is like a transverse field Ising model, basically. Your transverse field is your, Rabi frequency that, excites you to the Rydberg state, and you can break that with break that symmetry with a detuning. So that's like your magnetic field, your longitudinal field. And then you have this diagonal interaction, which is, this is my Vij in terms of a distance. It's a 1 over R6 van der Waals type interaction. Okay, so they're basically big dipoles, and then, they turn into van der Waals 1 over R6 when they're interacting. So that is really my last point. My point there is that this is where the entanglement comes from. If you have an arbitrary lattice of optical tweezers and you excite these atoms, at some radius, which you quantify with, they call it the Rydberg blockade or the blockade radius. It's very energetically costly to excite 2 of these atoms. Okay. So there's as you increase the detuning, it's negative, so I want more excited atoms. You get into this competition with the fact that, there's this interaction term. That's where all the interesting physics and entanglement essentially comes from, okay? The off-diagonal piece is sigma x, which is, I didn't write the right sign, but it's stochastic. Does that mean anything to people? Stochastic? Yeah. Okay. So I didn't actually write it as being stochastic, but there's a trivial unitary that makes it stochastic. So what that means is all, the strict definition would be a minus sign here. So when all of the off-diagonal matrix elements are Hamiltonian or non-positive, okay, then you have no sign problem. So we can do quantum Monte Carlo for this, just for the ground state. And also the Perrin-Frobenius theorem implies that the ground state, even in the experiment, is real and positive. So the extremal eigenvectors of that matrix are real and positive. So that's an incredible simplification that I'm going to use for most of the rest of my talk. So the states that I'm pulling out of these experiments, I'm going to assume that they're real positive. Okay? This is just an example of some of the arrays that can be built. Actually, this is already pretty old. I've seen much bigger 2-dimensional square lattice arrays. This is from the Harvard group. This is from the Harvard group. This is from the French group, in Paris. And of course, they can do 3-dimensional things, including an Eiffel Tower. So if you ever wanted to know how a quantum simulator performs on an array of Eiffel Towers, you can buy a machine to do it. Why is the data acquisition rate low? The data acquisition rate is low because there's a kind of complicated state preparation and readout for Rydberg atoms. So these optical tweezers are in some vacuum cell, and they throw rubidium at them, and there's basically a 50% chance that an atom lands in an optical tweezer. They have a feedback loop in the experiment where they take an image, and this is an actual image, that shows the positions of atoms, and then they detect which ones are filled and which ones are empty. And then they remove the empty tweezers and bring the filled tweezers together by physically moving these things. So there's a time scale associated with that. So there's a rearrangement step. Then once they're rearranged, they start interacting. And that's how the entanglement grows and how you build your quantum states and so on. And then after a certain amount of time, you take a snapshot of the qubit state using another laser. And this is, Rydberg states are just they're empty, but the atom's actually there. What happens is it gets blown out of the tweezer, and then the ground state fluoresces. Because you lose the atom in that single shot, you got to go back to step 1. So we took this data off of QEra's machine. This is Misha Lukin's setup. Manuel Andres got this working back in 2016. Here's a distribution of timing for shots. What's that say? Time per shot. Yeah. So that's where we're getting 3 shots a second, roughly. Depending on certain things, but the measurements are destructive. In a trapped ion setup, by comparison, you typically don't blow the atoms out of the trap. You just collapse the state. So blowing these things out of the optical tweezers is, in some sense, what kills you. Nonetheless, I mean, you get an incredible amount of data off of these machines. And I really got interested when I saw this paper in 2017, was it, that showed really, again, as a condensed matter theorist, a phase diagram that is a function of this detuning, off resonance, and the interaction range defined by, it's the distance between all of the, each pair of atoms or something. I see a really typical kind of condensed matter phase diagram where you have what they call a disordered state on the left here, which is all atoms in their ground state. And then depending on the interaction range, you can get Z2, Z3, Z4 ordered states. So long story short, Giacomo Torlai and Brian Timar, who was a student with Manuel Endres, up here in Caltech, basically after we saw this experiment, we were wondering, well, it would be nice to reconstruct observables from the data, but because the data is sparse, and this is not sophisticated, but for a different audience maybe. If I could build a frequency histogram, I could just calculate anything I wanted, but I can't. I have sparse data. I only have one shot a second. And so we wondered if there's any benefit to training models, because you have this implicit bias in the model, right? Here's samples from a Gaussian, and if I fit the red thing with 2 parameters, and it fits fairly well, obviously that's going to get me better generative properties than if I just try to, if I have no parameterization, let me put it that way. So indeed, the students looked at huge fidelity improvements, when you're using models. So this has really kickstarted this idea of using generative models. I'm almost out of time, but I'll just show you a few examples. So this is real data from 8 atoms, 3,000 shots, which is fairly, I would call it informationally complete, if you can say that for things that are occurring on one basis. But really what's going on here is, here's an experimental curve of the average occupation. And I should mention that these things are adiabatically prepared. You kind of tune them from disordered into the ordered state and then stop and take a shot wherever you want. So here's different stopping points and they collect data. It's only 8 atoms, so we can do a full time evolution of that adiabatic process. And here is a reconstruction with actually an RBM. This is small enough and RBM works really well. Works perfectly in the diagonal sense. Why would you ever do this? I mean, one point is that once you have the parameterized model, when you have an explicit representation of the wave function in this case, you can use these tricks that we use all the time in classical simulation, if you will, or variational Monte Carlo. One of them being the idea of a local estimator, which lets you measure off-diagonal expectation values, given at least the ratio of the wave function in these 2 different states. So from that, we can access sigma x, which is off-diagonal in the computational basis, and also things like entanglement entropies, like second Renyi entropies, or basically anything you want. So once you train one of these models, it's incredibly flexible. And to answer the question somebody said yesterday about what do physicists want, what we wanted here and what we got was we saw a discrepancy between the exact diagonalization, the exact state preparation the experimentalists were aiming for, and what we reconstructed. This never made it into the paper because we went back to them and they fixed it. It turned out to be some laser problem. But really, this is part of the. I like it because it's an illustration of how we use this, to build better quantum computers, if you will.
So can I ask, the RBM is completely simulated without any quantum input, or how do you create?
The RBM is trained from the quantum data that comes out of the experiment. That's what I meant. It's trained off of these types of shots.
Okay, that makes a lot of sense. But how do you then compare it with the actual experiment? Well, that is.
Oh, that's just the distribution. That's just like the frequency distribution here. That's just taking actual experimental shots in the same basis and calculating the expectation value of that. And that's what I'm saying is they should be exactly the same, especially in that basis, or else,
Or else there's a mistake.
There's some problem, yeah. So it's almost too simple. But what I wanted to emphasize was that you can get essentially any observable where this local estimator is sufficiently sparse, whatever that means. So you can get more than you can just get by directly looking at the experimental, frequency distribution.
And here you're just plotting them goes to show that you didn't make a mistake in interpreting the data. Is that correct?
I think so. Yeah.
So isn't the frequency distribution just p lambda in this case?
Well, if you have enough shots, yeah. Like that's how you would estimate that's how you'd estimate without any parameters.
Right, okay, so you're saying that you have way fewer shots, but you're still able to
Yeah.
find this. Okay, got it.
So it's more evident in 2D. So in 2D, now we have, this is an experimental phase diagram. So this is a two-dimensional square lattice array. This is a subsequent experiment. This is the same idea, this lobe, as the Z2 lobe that I showed here, but it's two-dimensional, so it's like a checkerboard state. I should have put that there. By the way, what's incredibly interesting for me is that there's a quantum critical point here, and that quantum critical point, is between a disordered and a Z2 checkerboard state, so you know the symmetries of the order parameter. So you know that it's in the 2+1 dimensional Wilson-Fisher fixed point universality class. And we would typically study that through a three-dimensional field theory, 2+1. But here is an actual two-dimensional quantum system that shows, I don't have it, but they extracted the critical exponents for the 3D Wilson-Fisher universality class. That's the first time that's been done. So the correspondence between a 2+1D system and a 3D classical field theory, which we take for granted every day. I mean, you could say that this is the first time it's been tested with a real quantum computer, and I think that's amazing. So I've been obsessive about this critical point and getting data from this machine to characterize it. And there's all sorts of interesting data that I got from the experimentalists for different sweep rates into this lobe and so on, different state preparation protocols. But just let me show you what happens when you don't have enough data. So here's 256 qubits, and we're kind of traversing this critical point here. And all the experimentalists took in their slowest adiabatic state preparation protocol was 1,000 projective measurements, okay, per detuning parameter that you see each one of these here. So now we do the same thing. I take that data and I try to learn the underlying pure wave function. I'm assuming it's all pure. And it doesn't work like the previous slide. I can't get any of my estimators to correspond. And the reason is, you can see if you look at the evolution of the loss function, and sorry, I cut it off a bit here, but you rapidly go down as a function of training steps, and then at some point start to overfit. And I have a quantum Monte Carlo for this system, and so I kind of know roughly where the energy should be, and you're not getting anywhere close to it. So that's what happens when you don't have enough data, when you're data limited. So then, to answer my question that I posed right at the start, what value is limited data, really? So Skylar Moss and Steph Zizek and other people that worked on this really found one interesting case for value proposition, if I can call it that. And that's to speed up variational simulation. So let me show you another curve, which is a different loss function. This is the same architecture. This is some sort of two-dimensional RNN. I didn't even mention what it is. There's a certain number of weights and biases. And you can treat that thing variationally, and you can get an improving loss function, which is, in this case, the energy. Oh, it was always the energy. And you can see that I'm slowly converging to the correct ground state. And it actually occurs at a much slower rate in some sense than if I'm optimizing with data. So what Skylar and Steph and other people observed is that if you took the data from the experiment, okay, and this is at some point on the phase diagram, and you start with a data-driven loss, and then at some point, and here's many different choices for which point you do it, you transition to the variational loss, you get a rapid increase in improvement or in the training, a rapid jump towards convergence here. So you can kind of quantify this and say, what's my improvement of my time to convergence? And I just pick a threshold for the energy, but you can do anything arbitrarily. And you can say, how does that improve as a function of this kind of transition time? And so this is a protocol that, I actually forget what they call it now. Data-enhanced variational Monte Carlo, it's right there. So you take data, you train a language model, whatever you want, with shots from the data, and then at some transition time, you switch the cost function to be Hamiltonian-driven. And what do? You get order of magnitude time to improvement for the variational procedure, okay? So you might say, why would you do that? I mean, that's interesting, and it's an interesting use of the data. But in this case, I have the ground truth through quantum Monte Carlo because it's not sign problematic. So my pitch to SAN specifically, is that you could take this and do it on a model where we don't have the ground truth, or a Hamiltonian where we don't have the ground truth. So for example, a frustrated model, something that they can actually prepare in the French experiments, like an XXZ model. Here there's no, it's non-stochastic? It's not stochastic. I don't know. It's quastic? I don't know, whatever. And so there is no quantum Monte Carlo, or the Hubbard model, where there is no sign-free Monte Carlo. And variational methods, for years, people have seen slow convergence. So my pitch, again, for the value proposition for quantum data, even if it's severely limited, is sort of early phase training for all of these variational methods that we've been struggling with in condensed matter for years, essentially. So if you can prepare a quantum computer that, is like a gas microscope quantum computer like SN works on, that prepares states of the Hubbard model, and you can get some data, even if it's limited in the number of bases and number of shots, you can get, again, orders of magnitude improvement potentially on the time to convergence for classical simulation algorithms. And so I think that's probably in practice going to be the first time we see, in some sense, I don't know, you can call it quantum advantage, but it's certainly value coming from the quantum data.
So here you have snapshots of spin ups and downs, but for something like the Hubbard model, you have spin and charge.
Yeah.
So does that mean you need both types of snapshots, spin snapshots and charge snapshots?
I think you should put as many samples in as you can get. Yeah. Yeah. Like if you think of a spin system, again, you have multiple bases, and there it's just two different bases in some sense, right? So you would want to train as much of the phase as you could from data, if you could train the phase.
But they have to be treated differently as the input to the RNN somehow. But you're saying that is possible.
You can handle that, yeah.
So, I mean, first of all, I think this is really impressive, but this switch from orange to blue, right, is something you observed that it works, and can you also prove that if you do that, it has to?
That's your job, guys. I have no proofs here that this works. And if I switch the order, it doesn't work, by the way. So if I do blue first, then orange, forget about it.
So, but somehow even finding any kind of theory which corroborates that would certainly be very valuable, right?
Yeah, I'm the experimentalist here showing you the behavior of this. And this is, I think, I don't know why. I mean, intuitively, you have the state, the target state, and you draw samples from it. And so when you drive the parameters of the model with that data, makes sense that it's valuable, right? It gets you towards what you want. Whereas the Hamiltonian is much more difficult. You have to measure the expectation value of the Hamiltonian in some sense in the variational cost function. So I think it's just much harder for many different reasons. But no, I've no.
It contains more information. Right?
Exactly.
Also, absolutely love this, and for the significance, maybe for the broader discussion we had at this conference, like quantum machine learning. Okay, what could be good about it one day? Might just be that it, these types of approaches, that quantum computing is much better if we use data to find the initial states, right? I mean, that's a combination that I have.
Absolutely. I mean, you built the oracle at some point there. It's giving you samples of what you wanted, and those samples are intrinsically certainly valuable for driving a model of that oracle. I don't know what you would say, but I'm glad you like it. Just last slide, just to bring things back to language models. The natural evolution of what we're doing basically looks like something like this. And this is a model we're training, and sorry, I have it on a private repo, so I can't give it to you yet, but we call it Rydberg GPT. This is the classic encoder-decoder transformer model. Now, the prompt is the Hamiltonian, okay, with all the interactions, Vij. The input of the decoder is the sample that I pull from the experiment. Okay, so I know my laser knobs, I tune them, and I get a sample out of the experiment. That's one element of my training set. This prompt goes in through the typical mechanism, whatever. We have one slight detail about graph embedding just to make this fit as a prompt. You have a latent space coming out of the encoder. You have the decoder architecture, and I've mostly been talking about decoder architectures now. And out of the top of the decoder architecture, you get the conditional distributions, which you multiply together to get the wave function, okay? So you can now use this in the same way you use ChatGPT. Literally, it's the same architecture. And so what do? You prompt it. So here's an example that we've trained off of data that is near the critical point again, or across the critical point, I should say. Here's the quantum critical point in the 2D square lattice data. The red arrows are the training parameters, if you will. So delta is part of the prompt. So I send the prompt in, and then I have the data to train the thing. And then after the thing's trained, I can vary the prompt. All you do is prompt it, just like you, I don't know, I never use ChatGPT, but just like you would use. And so this whole talk was written. So all of the blue curves here, or all of the blue dots, are the results of calculating the energy using those prompts. And so you can see these are all out of distribution, right? We've never trained on any of these blue points here, but the exact energy curve that I get from quantum Monte Carlo is behind it. So it's perfect. It works perfect. And you can extend this to anything you have in the prompt. We actually have an extended prompt with a temperature, like an effective temperature, different geometries of the lattice. And how well does it work? It works as good as you send, as you scale it. The more data you put into this thing, the better it works, just like GPT, whatever, right? And so this is a project. This is David Fitzek, who did the architecture in Chalmers. Yi Hong was an experimentalist in the trapped ion labs until I rescued him. He's now my PhD student. And Gibri, who works with us at Perimeter. So that's Rydberg GPT, and I think this is the future. Training these models and pushing the experimental data into them while you build these big models up and prompting them. It's an incredibly useful tool, especially I'd say for the experimentalists. I'm out of time. You can do things with complex states, but I mean, the only big difference is you're training a phase. So you just have to extend. I mean, it sounds easy when I say it, but a lot of details there. I'd say a lot of research. Marika, I didn't get to this, but we've also checked these models using classical shadow data. Bottom line there is if you have data coming from a computer, you're data limited, and you perform classical shadows, the reconstruction of estimators, it's always better, or you'll always get improvements by taking that same amount of data and training a model. I think that's basically always true. And I'll talk to anyone who's interested in this, but there's explicit differences. There's differences in the slope of sample complexity versus error that occur when you train models versus that you get from shadows. So this is known analytically, this scaling, but we observed scaling empirically in the autoregressive models, which is different, and there's no theories for this stuff. So again, just with my experimental hat on. So my point, again, unprocessed experimental measurements. They're coming out of the devices. They should be organized as training data sets, I would argue. You can train models, and you have scalable model architectures, so why not just continue the training and build foundation models out of them? So that's what we'll do with the Rydberg experiments. We'll basically build large parameterized models based on the training data that comes out of the device, and then you can prompt them. We want those things to demonstrate scaling, so we need tons of data, which is fine. Data's coming out of these machines. And the goal is to see emergence somehow. I don't know how that's going to look, but really, we want to see superconductivity emerge in the Hubbard model. This is how I imagine you would do it. What I almost never talked about was the heuristics involved in the learning. And what machine learning is great at doing is taking all of these hard questions and just putting them in some some stochastic gradient descent, and we hope it optimizes through heuristics. That's still true here. So everything we've done in some sense is heuristic optimization. But again, that's the future. And so here's just my little model of how we're already using these things to, in distribution, you can fit parameterized models for characterization control. Out of distribution, you can essentially extrapolate and help in the design and so on. So this feedback loop is essentially already enabled for the Rydberg atoms. And so we hope to see more of that in the future. Sorry for talking long. Thank you very much.